So our next topic that we want to dive into is concentration. Now, really, you have already seen this. We have already used this some in lab, especially when we had those big capital M on some of our reagent bottles. So some of you were using 0.1 molar HCl. Some of you were using 3 molar HCl, different concentrations in lab. Now we're going to talk about what that's all about, what we're doing there. So let's start out talking about just an idea of percent. It's kind of easy to digest this idea. Just thinking about what percentage of a solution is your solute of interest. I'm going to get the definition of solute in a minute, but the stuff that you dissolve in it. So you can think of something. Let's say that we're going to look at percent of sugar in a drink, right? So we're going to talk about the Kool-Aid you made and what percentage sugar was in it, or you could talk about what percent of a solution was salt for a salt water or something like that. So at the very beginning, that seems, oh well, that's easy to think of, and then that's easy to use. But then we have to get, of course we do because it's chemistry, right? We have to get a little more complicated with that, right? So now, first I have to ask, how did you calculate your percentage, right? So let's say we're talking about that sugar in water. Did you weigh your sugar? I mean, that's fairly likely, right? So if you weighed your sugar, you know how many grams it is. Did you also weigh your solution, or maybe did you just measure the volume of your solution? Well, now if you measured volume, now we're talking about different things, right? And so we have to start to get a little more precise on our units here. Are we talking about percent on the basis of mass divided by mass? So that would be like grams of sugar in grams of solution. Or did you look at, it was like 1 milliliter of sugar, which would be kind of strange to measure, right? Over in 1 milliliter, or how many milliliters of solution. So you could do a percent by mass, you could do a percent by volume, or this is done sometimes. I don't like it particularly, however, it is done where you do a percent M/V, meaning that you've taken a mass of your solute, sugar in this example, divided by volume of your water, and you want that to be in, this is why I don't like it, you need that to be in units that kind of work, and so the density of your solution / solvent matters here, and it starts to, our careful usage of terms starts to break down here. This is why I don't like using this version. So you'll see, though, even though this percent idea might seem like it would be an easy way to approach to start with, and it can be fairly easy to calculate, right? But we don't usually use that in chemistry for a couple of reasons. One being that the percentages of our solutions are often quite low. So this statement down here would be hard going to use this kind of thing all the time in lab. And then of course there's the problem of which version of percent did you use to calculate this, because sometimes it might matter. So even though you can think of this in terms of percent to kind of conceptually wrap your head around what we're talking about with concentration, it's not going to be the units that we actually use. Okay, much more common is for us to use molarity. Now, chemistry is famous for its molarity. We're going to use this all the time. So of all the concentration units, I care more about molarity than any of the others that I'm going to tell you about, including percent composition. Molarity you are going to see over and over again. If you take two chemistries, you're going to see it all through both of those chemistries. If you take more than 2 chemistries, you're going to see it in every one of them. I'm trying to think. It's hard to guess whether or not you would see it in one particular course called Physical Chemistry 2, which is all about quantum. Other than that, you will see it in absolutely every chemistry course. It's so incredibly important to the way we do chemistry. All right, so molarity is symbolized by a capital M. And remember, my triple equal means is defined as. So molarity is defined as moles per liter. Liter's -1, so it's in the bottom. So let me just rewrite that to make sure. Molarity equals moles over liters. Okay, and it's moles per liter of total solution, not necessarily solvent. We'll get to that in a second. But it's, so once you've made up the thing, well, my total solution volume is 500 milliliters, so 0.5 liters. Cool. And I've got 2 moles in there, right? 2 moles in 0.5 liters. So 2 divided by 0.5 would give me 4. So that would be a 4 molar solution. Okay. It's by far the most common. And okay, so I wanted to define some terms here. So I'm going to use these probably without thinking about them, but a solute. Solute is the thing being dissolved. Solvent is the material doing the dissolving. So it's usually water or an organic solvent. So we used water in the lab. Sugar was our solute and water was our solvent. And then solution is put together. So sugar solute, water solvent, and sugar water solution. So the solution is actually after it's dissolved and you've made up the solution. And unfortunately, there are confusing bits that go with this. So molarity was moles per liter, and molality, which is a little m, is moles per kilogram. And technically, it's even more confusing because it's kilogram of solvent, not of solution. We're not going to use molality. It gets used some in quantitative work. But if you do your quant here at Dalton, we rarely use molality there either. I don't know who uses molality now, but just know that it exists. Sometimes it gets thrown out there on exams when we steal questions like you've seen me do before without thinking about it. Ask me if I use a molality thing, because I probably didn't mean to. It is a little bit in Chapter 11, so you might see it in Gen Chem 2. So that this way you can look back at your notes from this one and see what molality was if you encounter it later on. Let's see. Now, there's not much numerical difference when you're looking at dilute solutions, but when you're looking at concentrated solutions, the numbers can be significantly different. Another concentration type is normality, and I couldn't find this one in your textbook at all. Let me know, somebody, if you do find it. It's capital N, and so it's a little more confusing. This is usually used with acids and sometimes with charged species like ionic solutions and stuff like that. So it's moles of charge equivalents per liter. So the simple way to look at this is if you've got a doubled charge, you just double your molarity. So it's just like calculating molarity, but then you're just adjusting for the charge. So like a 1 molar calcium 2+ solution, 1 molar would be 2 normal because you're just multiplying by the charge equivalence. Like I said, I usually see this used with acids. You're not going to encounter this any further in Gen Chem 1. You'll sometimes see these in, like, especially I've usually seen it in an environmental context. Maybe it's engineering in general, but certainly in environmental engineering, you see this a lot. So sustainability majors, I suspect you're going to run into this a lot in your career. ppb and ppm, which stand for parts per billion and parts per million.
So it's a lot like percent, except that we're dealing with solution, not solvent. So what it means, 1 ppm is 1 part per million, right? Or like 1 times 10 to the negative 6th grams of solute per gram of solution. So like 1 gram solute, or 1 gram of solute per million grams of solution. And I went ahead and mixed these here, not on purpose. I just did it because usually this is not really corrected for mass, and you're talking about milliliters instead of grams. So 1 microgram per milliliter is the same thing as a ppm. Now, a ppb, parts per billion, is just going billions instead. So 1 billionth of a gram per gram, or 1 gram per billion grams. Microgram per liter, or a nanogram per milliliter. Okay, and technically there's so PPT I didn't put on here because it can be confusing. You could use PPT to mean parts per thousand. I would not have said that. More commonly, I would have said that PPT means parts per trillion, so it just goes to the next level down, nanograms per liter or picograms per milliliter. So the trillion versus thousand is why I wouldn't use it, but technically I think I would use, instead of parts per trillion, I would use a per mil, like percent. So anyway, just know that there's some confusing things out there. PPB and PPM are the ones that you might actually run into. All right, so let's talk about calculating percentages, and we're going to step back to the ionic solids side for right now, or ionic compounds at least. All right, so let's ask what percent by mass of sodium chloride is the sodium part, right? All right, so how would we do that? Well, we need to know its total mass, right? So I'm going to look on so let's just consider 1 mole of it, and then we can use the stuff straight from the table. So for 1 mole, I've got 22.990 grams of sodium. And then I've also got, let's see, I've got this, so it's 1 sodium and it's 1 chloride. So I've got that plus 35.453 grams of chloride. So I get a total of 58 point, what did I get? 58.443. Is that enough? Yeah. 443 grams total, right? But now I want to know just about the sodium part, right? So sodium was this mass here, right? So to find a percentage, I'm going to take that, 22.990 grams divided by my total mass, 58.443 grams, and I'm going to get 0.339. Oh, 39. 3375. All right, now I got to turn it into a percent. I'm going to go ahead and do my sig figs at the same time. How many do I have? So I've got 1, 2, 3, 4, 5, and I've got 5. So I can have 5. 1, 3, 4, 5. So I got to stop here. So 39.338% sodium. All right. So that's how I'm going to calculate the percent of a compound. So for molecular compounds, this is going to work the same way. Now, in this case, let's see, I'm asking, what percent by mass of propane is carbon? Now, I guess you do need to know, and y'all don't have any way yet. So, propane is C3H8. All right, so we're going to use that just like we did the sodium and the chloride in the previous slide in order to calculate this. So let's see. Total mass, I've got 3 times the carbon mass, 12.011. All right, and now I'm going to add that hydrogen mass, which is 8 times 1.00794 grams. And we get a total mass here of 44.0965. All right. Well, let's see. I need grams there. Now, what do I have? I want to know about the carbon part, right? So that's this. All right, so that's 36.033. Divided by total mass, 44.0965. And you're going to get, so let's see, that divided by that, I get 0.817139. Let's see, I had 5 sigs there, more than 5 there. And remember that remember that the coefficients are exactly 3 carbons. So you don't have to include that in your sig fig stuff. So I just need those masses. That was 5, and that was more than 5, so I get to keep 5. Let's see, actually, did I do that right? So, yeah. So really, I can't be sure after that. But that's still 5. Okay, 1, 2, 3, 4, 5. So I got to stop right there. 81.714%. And I want to mention too that on the homeworks, a lot of y'all are getting beat up on points on sig figs. Sig figs do not go away, so you should always consider them in every chemistry calculation. All right, so you see how we get this 81.714%. And I'll point out that, look at this, we've got 11 atoms in this molecule. Only 3 of them are carbon, but the carbon is 81.7% of the mass because carbon is so much heavier than hydrogen. So make it make sense in your head too. Okay, now for going backwards. Now prepare yourself because this one's going to be a little crunchier. It's going to take a little bit of doing, and you may have to rewatch this piece multiple times to get there, and I can do other practice ones if you want. So what really happens in chemistry is we'll do an analysis and we'll get a mass breakdown. Let's say that we have a sample, and it comes out as 83.236% carbon and 16.764% hydrogen. Now you could do some other mass if you want to, but there's no reason to make it more difficult than it already is. Let's consider a 100 gram sample. And for a 100 gram sample, we can just turn each of these percentages into grams because 16.764% times 100 grams is 16.764 grams. Okay, so that's the first trick. So I'm turning my percentages into grams by considering a 100-gram sample. Okay. Now, the coefficients in a molecule are not based on mass, they're based on moles. So we need to see, in each of these cases, how many moles of these things there are. So to do that, I'm going to need, from the table, let's say we've got 83.236 grams of carbon. How many moles of carbon is that? So I need, from the table, 1 mole. Look on the table and get from carbon is 12.011 grams. Now, again, and you've seen me do this many times, my grams on bottom here because I wanted to cancel, right? All right, so crunch those numbers, and I get, what did I get? I got 6.92998. All right, we're going to come back to this in a minute. Let's go ahead and do the hydrogen part, and we'll come back. All right, so hydrogen, I've got 16.764 grams times, from the table again, 1 mole per 1.00794 grams. And I get, what did I get? 16.6319. Okay, those are moles. Should put moles over here too. So those are moles in a 100-gram sample. All right, but now we really care about the ratios, right? So here's the second big trick. You find the smaller amount of moles. In this case, it is going to be moles of carbon, and you divide everything by that number. What you're doing, this is called normalizing. You're normalizing to that smaller number. Now, automatically, your smaller one is going to become a 1. That's what normalizing does. Okay, but then your other, and so, sometimes it's not just 2. In this case, it's just 2, but sometimes it'll be more than that. But it won't be a 1 or an even number usually. We're going to need to make it 1. So we're going to get, let me go back to blue here, 1 mole of carbon here. And we're going to get, what do we get on the other? Let's see, I got 2.4. Now, unless you are a geologist, you do not use decimals in your chemical formulas. In geology, we actually do. So in chemistry, don't do that. Don't do that. Chemists don't handle it very well. So we're going to need to change this up. So I need to multiply this by some number to get an even number. So 2.4 times something will give me an even number, and you're just going to have to do trial and error on this. You can do times 2, you get 4.8. Nope. You can do times 3 and get 7.2. Nope, that didn't work. Keep going, you'll find that times 5, right? So if you do this times 5, you get 12. So and all this is some mole accounting tricks. Well, I multiplied that one by 5. I got to be fair and also multiply this one by 5 and get 5 moles of carbon. And lo and behold, we have snuck up on a we snuck up on an empirical formula. Here's the word I'm saying, empirical. An empirical formula of C5H12. All right, so this could be, in fact, pentane, which has 5 carbons and 12 hydrogens. So I made up the numbers based on pentane, but technically this is an empirical formula. You don't know. This could actually be C10H24, which does exist. It could be C15H36, which pretty likely exists. So all you know is the ratio here, but the simplest of those would be C5H12. This is how you determine an empirical formula, and you're going to have to crunch this math. So please run through this calculation again and make sure you can get it, because you know that you're going to see it on a homework. Okay? All right, another bit of calculation that we need to do. Now, what do we use M for? What does it mean? It means molar, right? Okay. And what do we use molar for? So this is solution concentration. And I'm going to use brackets. All right. Brackets means concentration. You'll see me actually abbreviate all the time. So this is solution concentration. All right. So let's see, how is molar defined? Let's look back at that slide, and I think it is defined as moles of solute per liters of solution. All right, so moles. All right, moles of solute. I've got my moles of solute. I can use that. Okay, but I don't have liters here. I've got milliliters. So 56.78 milliliters, and if you can do this in your head, that's even better. 1 liter per 1,000 milliliters. Right. So how many places moves it? 3. So it's 0.0567 Don't go to rounding off too quickly now, right? Because you don't want to lose your sigs. We've got 4 sigs in each of those. We'll keep them. All right, so now I can do my moles of solute. So 1 point, that's a terrible point. 1.234 moles divided by 0.05678. Oh, I should have put liters on the end of this because mils canceled out, leaving liters. What I can clean it up there. Divided by liters. All right. So I'm going to crunch those numbers right quick. So 1 point, it's going to be a large number. 1.234 divided by 0.05678. 21.7 molar. That's an extremely concentrated solution. 21 point, how many do I have? 4.673 moles per liter. Big capital M. 21.73 molar. All right. You'll see that for your homework as well. All right, we're going to calculate a molar concentration again, but I mean, even though this problem looks like the previous one, this is going to get a much, much smaller value because here I do not have moles of sodium chloride. I've got grams of sodium chloride. And watch how different an answer we get out of this. So molar is still moles per liter, so I've got to turn this into moles first. All right? So I've got 1.234 grams, right? And then I've got to multiply by 1 mole per, what was that? Let's see, it was 22.990 plus 35.453. I'm going to put that in parentheses down here. Grams. All right. So 1.234 divided by 22.990 plus 35.453. So I get 0. Oops, I forgot a 0. 0.02. 1115 moles of solute sodium chloride in this case. Now we still know this 0.05678 liters from before, so now we can plug all that in. 0.021115 moles divided by 0.05678 liters. This time I get a much more reasonable concentration of 0.373719. All right, so instead of 20 molar, I'm looking at 0.4 molar. So make sure you can calculate that given moles or given grams. If you don't understand what I did differently, we need to talk. It has to do with converting it to the moles in the first place. All right, now I want to talk about a very, very important, simple equation, but very important. Okay, and this says that you can rearrange and calculate any new concentration given an old concentration and volume and a new volume, or any one of the 4 missing variables. All you've got to do is rearrange this equation. All right, so let's see. Let's try to dissect this word problem. What are we going to do here? We're going to take a 30 milliliter aliquot. That just means to take a bit out of. So an aliquot is just a subsample. Like we're going to take 30 mils out of what was originally, so this blue solution here is originally a 1.234 molar solution. All right, so we're going to take this 30 mil subsample, just a little bit of it. We're going to take it over to another container, right? And we're going to dilute that to a new 1,000 mils total. All right, so we're going to pour that in a new one and then dilute it up to a 1,000 mark. All right, and so we want to know what the new concentration for that is. All right, so here's how this works. So do we know C1? Well, yes, here it is. So this one is going to be my C1. So I'm going to put a check mark over it. I know that. All right, here I took a volume out right here. So that was the initial volume, V1. So I know that. All right, do we know a concentration 2? Let's see. Now, what is the resulting concentration? So we don't know that. All right, I'm going to circle it. That's what we don't know. We better know that last one. Let's see. Oh, all right, so we diluted it to 1,000 mils total. So, no, see, that's a V. So this will be our final volume, or V2. All right, so good. We've got 3 of the 4 pieces we can solve for the other one. All right, so remember your maths. Your maths are not going to go away. They're going to haunt you all semester. All right, so I want to get the C2 by itself. So C1 V1 equals C2 V2. Now, if I want that V2 to go away, I need to divide by V2 so that it'll cancel. But if you do something on one side of an equation, you have to do it on the other. So that cancels. That leaves me C1 V1 over V2 equals my target C2. Okay, well now all I have to do is plug in C2. Let's plug in the pieces that we know. So let's see, C1, what was my C1? It was 1.234 molar. All right. Oh, y'all watch and see what happens with my units. They better work out, or otherwise you guys get to yell at me about this, right? Let's see. Do we have another piece? What else is on top? V1. What was V1? 30.00 mils. All right. Let's see. V2 down here. V2 goes on the bottom. 1,000 mils. Technically 1,000.0 mils. All right. Now, what will cancel? Let's see. Mils on top, mils on bottom cancels, leaving me molar, which will be a concentration unit. Yay. That's good. That's what we want it to be. All right. So now you got to crunch the numbers. So 1.234 times 30 divided by 1,000. So 0.03702 molar. All right. So do I get to keep all those? 2, 3. I should have 4 there. Let's see, 4, 5. Yep, I get to keep all of those. And don't be confused, because I will do this. I will use the metric prefixes of that. So that is 37.02. Watch what I do here. Millimolar, right? 37.02 times 10 to the negative third molar. 37.02 times 37.02 millimolar, or 0.03702 molar. All of those are precisely the same answer. All right, so make sure this works out. Let's see, a big trick that you'll run into. In our case here, we had milliliters and we had milliliters, so they cancel out. But I could as easily have done this as 1.000 liters, in which case you would have to convert it to milliliters first, make sure that your volumes are in the same units, or make sure that your concentrations are in the same unit when that comes to pass. Remember that you could solve for any one of these, right? You can isolate any one of those using your algebras, okay? Let me know. You're going to see this over and over again, both in lab and on exam 2. This stuff is all in chemistry. If you take any more chemistries from this, any other chemistry professor is going to come and yell at me and hit me with things if I don't teach you C1V1 equals C2V2.
Okay, so that'll end us up for this video. Now, we'll have next video lecture is going to be chemical equations and stoichiometry. That's how you say it, stoichiometry. And so we're finally getting into some really fun stuff with this. I want to tell you here for the next bit. So the next lecture is really going to be about 4.1 and 4.3, but I really think that it will go more smoothly if you'll take your textbook. Now these units, these sections here, they're not very long. So if you'll take and you'll read through chapter 4, all the bits of chapter 4, it's really going to get covered in a couple of different video lectures, but if you'll read the whole thing first, and then we'll get into the chemical equations and the stoichiometry part, I think having a little bit of the class of the types of reactions is going to help a lot to follow the stoichiometry part as well. And then, of course, I will likely ask you to reread some sections later on just to reinforce it before the next one. But the stoichiometry is coming next, and I make the claim often that stoic is the #1 most important concept from General Chemistry 1. So know that I'm going to be hammering this one really hard. So get comfortable with the concentration stuff that we just did, because we're going to need it again for the stoichiometry. See you in class.